All right. So what do you want to do? Something about. I actually can't remember all of the problems. Something was about a hurricane. You had to find the energy. Let's do the last. I think it was the last problem first, because actually it was kind of fun,
Okay.
and it was about. He kind of mentioned at the end of the last class about like thermal.
That's 14. Thank you. You have it?
I
Yeah.
think it was like.
It's 3, 4, 7, 11, 13, 14.
Oh wait,
12.1.
it's not. Have you seen this before? MCAT? It's not an there's no A, but it's just what people call it MCAT. Well, my chemistry teacher called it MCAT. So maybe it was just him. Actually, I fell out of love with that marker. But anyway, so this is the amount of so I'm just writing this randomly, but I'll introduce it such that it ties to this problem. This is the amount of heat that an object gains or loses when it changes its temperature. It's actually not that, it's actually pretty intuitive, because you have here is the specific heat. And it better be, and here's the other thing too. Remember we talked about there's specific heat and there's like heat capacity and there's like molar heat capacity, whatever. It doesn't, of course they're all different, but if you just look at the units, you can tell which is the right ones, because this has units of joules. These are sort of corresponding. This has units of kilograms, obviously. And now and then delta T has units of Kelvin or degrees Celsius or whatever, right? So therefore, this specific heat C must have units of, I guess I'll write it again, N, C, delta T. So C, in the one that goes in here, must have units of what? Well, it has to be joules per
Kilogram Kelvin.
kilogram Kelvin, exactly. So if they tell you something about the specific heat is like joules per Kelvin, you know that it can't go in this formula. If they say just joules per Kelvin, you know that they've already accounted for how much mass they're using or whatever. Like if they say I have a pot of water and has this many joules per Kelvin, like in other words, to raise the temperature by 5 degrees requires 5 times this many joules or whatever, right? Or it cools, it gives off that much heat or whatever. That would be they're already accounting for how much there is, right? Because otherwise, how could they know how much, right? If you double the amount of water, you need more heat.
Is that still specific heat?
That would be called heat capacity.
That's okay.
So that's where the words are important, because just for the same reason that all words are important. But the words are not as I don't like the words as much because they obscure. Heat capacity has units of joules per Kelvin, and specific heat. I don't know what I'm writing.
Got it.
I was so close. Specific heat has units of joules per kilogram Kelvin. So this is where I guess you really should know the words, but if you know what the units are and where they go, that's actually the important part. They just named them some stupid name because they couldn't think of anything else, I guess. But anyway, yeah.
Isn't that similar to how specific gravity works?
Yes. Oh, it's
exactly that's how I learned it.
Oh, okay.
I learned that
yes.
first, and then this came, and I was like,
yes.
Oh, that's what that means. Okay.
Yeah, it's basically exactly the same.
Okay.
Yeah. Right. So a lot. It's kind of like he was talking about extrinsic and intrinsic quantities. I forgot if he said those words. Someone said them, and I don't know if he said it was right or wrong.
Okay.
It's right, but I don't know if it's what he was looking for. But the point is that there are some quantities that are intrinsic. Okay, now I'm going to forget what they. Intrinsic quantities, I believe, rely on just the material itself and doesn't have to do with how much there is. So it's just water has, I can't think of the density of water, for example. The density of water is an intrinsic quantity because it's just a property of water. The mass of water sort of doesn't mean anything. You might want to talk about the mass of a bucket of water, but then that would be an extrinsic quantity because it depends on the sample you have in front of you. It's not general to water.
Okay.
It doesn't, the fact that you have a bucket of water that weighs 1 kilogram has nothing to do with, it doesn't define water at all. You can't say water is the thing that when you put in a bucket weighs 1 kilogram. It's not true. Water is the thing that has a density of this thing. So intrinsic would be like this one. This is intrinsic because it depends on the material only.
Right.
This is extrinsic because it depends on how much you have. So actually, and you can kind of see, I mean, we've kind of used them, that MC is the heat capacity. Right? So the mass times the specific heat is the heat capacity. You could also get the other one, which I'm not going to write because I'm going to forget where everything. Well, it would just be where you replace kilograms with moles or whatever. And all you would do to get to that is you just multiply the specific heat by kilograms per mole of whatever, and then that would have units of joules per mole Kelvin. Right. So that would be the specific heat times kilograms per mole is just a, like, it's not a,
Stoichiometry.
there you go. Stoichiometry, yes. It's something about, my chemistry teacher used to say, you can't spell stoichiometry without stoic. He thought that was funny. Anyway, but I guess I thought it was kind of funny too. But anyway, it's just, of course, you look it up.
Okay.
It's the what's I forgot
Molar
what this.
mass, the MU.
Yeah, molar mass. Like, is that okay? Molar mass, the mass of a mole.
Atomic mass.
Yes. Yeah, you could right. You could look it up from the atomic weight,
There you go.
which is in
All of the above.
atomic mass units,
Mm-hmm.
but then you have to convert to kilograms. Anyway, it's not a fun. It's just a lookup thing.
Not a good time.
It's not like a thing you derive from something else, right? Anyway, so the point is this would be the molar specific heat or molar heat capacity, whatever they call it. I don't know. Molar, I would call it molar specific heat, I think. But anyway, just keep in mind that in this equation that we're going to use, so I'm going to erase all this, but in the equation that we're going to use for like when things are melting, like ice is melting in water, which is I think what the problem is. We're going to use this equation, and this equation, of course, must reuse the sort of mass specific heat, meaning there has to be kilograms here because we have to multiply by m. Now, if the problem gives you how many moles there are, and you have to do something with this, you'd probably be best to just convert everything to kilograms. Like, don't try to combine it into that other variable and try to, like, I would just keep it as few sort of variables as you can. And so if something gives you something in, if the problem gives you something somehow in moles or moles here or something, I would just try to convert everything to kilograms. Just because you might as well know one equation and then convert everything to this equation as opposed to like trying to memorize like the equation with the conversion in it or something. Anyway, so the point is that this equation tells you how much heat an object requires to raise its temperature. Not an object, well, yeah, an object or like an amount of water or whatever. And so the problem that is in the, I think it's either the last one or the second to last one, is like they say there's some water and they say let's just say there's m water amount, mass of the water, and they put ice in it, m ice amount in it, and they tell you the temperature. I'll say T water and T ice, and then they say after a while, when everything's melted sufficiently, how much ice is left, basically. So then they say later it's they say at thermal equilibrium. Thermal equilibrium, how much ice is left. And the reason we're going to use this equation, so you'd see this problem. How do we know to use this type of equation? Well, by the first law of thermodynamics, we have that the change in energy, I guess you don't really need to use the first law, but I'll just connect it back to that. The change in energy is given by the work done by the system, it's given by the heat minus the work done by the system. There's no work in any of this because there's no gases, no pressure, or anything like that. Everything's kind of just sitting there, and the change in energy is going to should be zero. How do we see that it's zero? Nothing's flowing in and out from the outside, I guess, right? There's no like stuff flowing in or out. We're pretending this is an isolated system. So this is going to be zero. So it's really, I guess you could, it depends on how you say it, I guess. But the point I'm trying to, okay, let me erase this. the point I'm trying to make is that
That scared the crap out of
the,
me.
oh yeah,
Oh my god.
some trouble.
He's got it.
Like-
There you go.
Oh, there we go.
What are we talking
Oh, it's like a marionette. Anyway,
Just looked over. Scared me so bad. Sorry. Total
Okay.
tangent.
everything's okay. The change in heat is going to be 0 basically. You really okay? They don't really write change in heat. They usually use Q as change in heat, but to make it clear, I'm going to say change in heat 0. That means that really what it means is that the heat from the water goes into the ice. Which, when you say certain things, they sound like, well, obviously. But that's kind of thermodynamically what you'd say is happening. The heat, the Q heat, not just like heat abstract, but like the actual variable Q, from the water is going into the ice.
Instead of like the ice cooling down the water.
Yes, exactly. Because you can't talk about it the other way, right? I mean, you could redo all of thermodynamics
I'm good.
and talk about coldness if you prefer, which would be just exactly the opposite of everything. But you'd have to reinvent all the equations. I mean, it would probably just be minus Q. But anyway,
Not enjoy doing
don't do that. But I would say, yeah, so then let's think about what's actually happening. And actually, let me erase all of this. And I'll draw like the stages of what's happening, because this is a little harder than just conserving heat or something like that. Because what are the stages of what's happening? So, okay. I was thinking of a different one that I drew a nice picture of. Never mind, it's not this one. But let's just still draw it. So we can find I was thinking of a different one. Okay. We have the heat. So once there's ice in here, once there's ice in here, the temperature of the water is, basically they tell us at the end, there's going to be some ice left over, they tell us. Now we don't know that, but let's just pretend we know that for now because they tell us. A little bit of ice. Therefore, what temperature must this, if this is at thermal equilibrium, everything here must be at 0 degrees, right? So therefore, we know that some of the heat of the water is going into the ice, and it's going to be the amount to bring the temperature of the, so actually so we have M of water, C of water, and then it's going to be the initial temperature of the water. I guess it's kind of annoying that I'm not using numbers, but whatever, minus 273 Kelvin, I'll say. Because this is supposed to be 0 degrees, right, the freezing point. That's how much heat is given off by the water, right? The water cannot give off any more heat than that because it can't cool any further. So therefore, if the net change in energy is 0, that must be how much heat the ice gains. So this must be equal to the mass of the ice times C of ice times, and now this is going to be delta, this is going to be the change in temperature of the ice, so this is going to be T ice minus 273 Kelvin. Now this is actually going to be a negative number here. Oh, sorry. Yeah, you're right. It's sorry. You should put this backwards because it's really T final minus initial. The final temperature is going to be, sorry, this is going to be M melted. 273 Kelvin minus T ice. Sorry, you can tell this is not sort of a polished presentation of this problem because I kind of forgot. But, so let's go back again. So what do we have? We have on the left side, we have all the energy of the water.
Mm-hmm.
The water can only give up this much heat. right? That's what we've decided because it can only be at zero. It can only be at 273. Can't be any colder. So this is the total amount of heat it's going to give up until it's at thermal equilibrium. Once this amount is given up, it's at thermal equilibrium. So this is Q. Well, I won't write anything like that. And on this side, we're going to say, where does all the heat go, right? Because we're trying to figure out. Now, if I just write M ice, which I did a second ago, times C ice times this, I'm saying that that's equal to the amount of heat that the ice gets by melting, all of the mass of the ice. But we don't know that that's true because they told us that there's some ice left over. So definitely all the ice has not melted, right? So we just say that, well, there's some amount melted, M melted, I'll call it, but still has the same specific heat as ice. Same change in temperature. It was at, negative whatever Celsius, and then now it's at this temperature. This is final minus initial. And then here, we also have another thing because just to melt ice is, I should have done the other problem first, which I'll do right after this, but you need to take into account that there's that latent heat that he was talking about. So when you change the temperature, so if I put, I'll just put heat here, and temperature, actually, I guess I want to do it the other way. If I put temperature and heat here, energy here, as you increase the energy, your temperature is going to go up, but then at a certain point, you're going to increase the heat. You're going to give it more heat, but the temperature is not going to go up, right? And then you're going to get to another point. So this is going to be like when it's a solid, and this is going to be when it's a liquid. And in here, it's melting, right? And melting is literally a change in the actual configuration of the molecules. So and there's all these bonds that are broken. So the energy is actually going into all those breaking of bonds, but the temperature is going to be at this point, when this is called the freezing point, obviously, freezing temperature. And then at a certain point, when it becomes liquid, then it's going to boil. But there's and this is actually much longer than this for other reasons that are complicated. And this is when it's a gas, and this is going to be the boiling point. Boiling. Right, and this is going to be, again, some latent heat here. And I guess you could think of it as, from a solid to a liquid, you're breaking bonds from a sort of a crystal, right? Ice has like a crystal structure, and water does not. But water still has a bunch of hydrogen bonds that keep it a liquid. So you're basically breaking the sort of precise configuration of the I'm pretending that's water, and it's it's in like a hexagon. I don't know if this is really what it looks like, but somehow in like a hexagon, right? Let's just pretend.
Okay.
And there's another one, and then there's another one, there's another one. So they make hexagons, right? Like snowflakes. Anyway, so they make this crystal structure, and as you break them, you turn it into a liquid, but you don't have to break them completely, right? You're just breaking the specific configuration, but they still have 100 hydrogen bonds together. That's why they're a liquid. Otherwise, like, why don't they just fly over the place? Because they're stuck together mostly. It's just that they're not stuck together as sort of carefully. But then this one, you're actually breaking literally all of the hydrogen bonds, right? You're breaking all of them when you boil it. And so this takes a lot longer. That's pretty much true with like every material. The boiling, here, let me write it like this amount of heat here. This is an amount of Q heat, right? This is actually it's called, this axis is called Q. This is an amount called the latent heat of vaporization. And this one is called the latent heat of fusion. I guess because you go the other way and it's fusing to a solid or something. Anyway, so these are amounts of heat. They're Q values, but they're amounts that don't raise the temperature at all. So effectively, it's like here the specific heat is like infinite, kind of. It's kind of just because of the fact that, so it's kind of a strange thing. Like you wouldn't think of it like this. It seems like in physics, it seems like most things should kind of have smooth curves everywhere. So somehow the fact that because there's these different like structures that matter can be in, like solid, liquid, gas, you get these weird times when the specific heat changes to like infinity. Now it's sort of not surprising that the specific heat. Specific heat, remember, this is Q versus L. Or sorry, this is Q versus T, right? So the specific heat is somehow the slopes of these lines here, right? I guess it's the inverse slope because of how I've drawn it. But you can imagine why the slope of this line and the slope of this line, and the slope of this line might be different because, again, it's about the buckets, right? How many buckets can you put if you just throw energy into ice? How many buckets can you put in? Well, it can vibrate certain ways. It has a certain structure, so it can only vibrate certain ways, but it can't really move very much. Like most of the energy probably doesn't go into linear motion. It moves mostly into like the spring stuff. And this one, though, they can move in a bunch of directions, but they're still mostly bonded to make it sure it's a liquid. So there's some more energy places you could put energy in. And up here, you could put them into, it would just be like the ideal gas we've been talking about with the three-dimensional linear motion, and the vibrational of the, how the molecule is shaped, and then the 3 rotations. And so it's sort of very different places you can put energy in these places, and that's why, in these states of matter, and that's why the slopes of these are different. Because again, the slope is just like mc or 1 over mc maybe. And if we pretend the mass is all the same, but you could just say it's c. But again, the whole point of this diagram is that there's these places where the temperature does not increase at all when you put heat into it. So that's what we have to consider here, because we know that the water is going to stay water until the end. But the ice, some of the ice is going to melt, and it's not just, this is just heating the ice. This is just heating it to 0 degrees. So if we leave it like this, what we have is water at 0 degrees and ice at 0 degrees. And as we see, this point here is ice at 0 degrees, and this point here is water at 0 degrees. Right? So what we've done is taken, using this diagram at the very beginning, we had an object here, that was the cup of water, and we had an object down here, that was the ice. And we've moved them to here. So we've taken into account, so these slopes are MCATs, right? The slopes are MCATs because we know that there's a sort of non-zero slope. And we've gotten to here. But now we have objects here and here. They're not at thermal equilibrium yet because they're at the same temperature, I guess. But they don't have the same, like, it's going to melt some of the ice. So what we're going to have is that because we know we have water, we have ice left over, we're going to have to move some of the ice all the way up to here. And so that's going to be, we're going to have to use the heat of fusion for the mass of the, so it's going to be, so what's the heat of fusion? It's going to be m times, oh wait, L is the heat of fusion. And I think L has units of joules per kilogram Kelvin. Is that right? So it'd probably just be the mass. So it's going to be some mass times the heat of fusion. What is the mass going to be, though? The mass is going to be the amount of ice that was melted. Oh, sorry. Yeah. Melted. So I guess, sorry, this should have been...
Is 1 m solid and 1 m melted?
Yeah.
Like ice remaining and ice melted or something?
Right. So I guess this one should be remaining. So I could write the,
You can do like m ice minus
Wait.
m melted or something.
actually, no, sorry, this should be the whole thing. Because all of the ice is going to get to 0.
Then
And then the rest is, yeah, okay. And then this is just the melted ice. Okay, sorry, yeah, this gets a little confusing, as you can tell.
you're good.
So now we have this equation. Now, in the problem, I think they have to give you the mass of the water and the mass of the ice that's used, right? And sea ice and sea water we can look up because those are just numbers that we can, they're well known. The temperatures they have to give you, of course, otherwise you can't do it. And the only thing we don't know is, and L is, you could look up for water as well, for ice into water. M melted, therefore, is just the mass that we're going to solve for, right? Now, this is just saying that, again, the difference between these two is sort of the amount of heat left over after all the water gives its heat to all the ice. So after all the ice gets to this point, after all the ice gets to this point, right, we're kind of meeting these here. If you subtract that, like if you take this thing and subtract it from this side, you'll get the leftover heat, right? The leftover heat is going to start melting the ice, right? So it's actually going to start melting some of the ice, and because we don't know how much is left over, we know L fusion. This has to be an unknown variable, and of course that's what they're asking you to solve for anyway. So that's good. So in other words, depending on how much more heat, if the water has a lot more heat than the ice, so if you use more water, right? Because if you use more water, M would go up, and so you'd have more heat here. Or if you use hotter water or whatever, I guess that's it. Then you'd have more heat in the water, and then you can subtract this, and you get more leftover heat to start melting the ice. So eventually, if this M melted becomes equal to M ice, then you just get that the whole thing's melted. And, that could be something. But of course, they tell you that it's not quite. So once they say melted, then of course the answer, I think, if they ask how much ice is left, you'd have to do M ice minus M melted. Right? This would be the leftover ice. Okay, does that make sense? The one I was going to do, which actually I think is a little, I like it better because I can draw a nice picture. But the one I was kind of thinking this was about, it was like an ice cube, and then you just start like heating it up until it turns to a certain temperature in water, and then they ask you how many joules does it take to do that. Is that
How long will it take to get the ice to 0?
or how long, and they tell you the watts or whatever.
Yeah, how long will it take at a constant power to
Good.
melt
Okay, yeah, that's a good one.
the ice?
Part B of 14, Keegan.
Sorry?
Part B of 14. It asks one we just did. It
Yeah.
asks, how does your answer change if instead of water, the liquid's 50 grams of 60 proof whiskey?
Oh, yes. Good to know. So then for the water, remember on the one side we had Q water, and it was going to equal, it was going to equal Q ice, but I would say it's like minus Q ice because the ice is gaining heat.
Mm-hmm.
Depends on, I guess, where you want the sign. But that was because we used T final minus T initial, so it was already negative. Anyway, plus the latent heat or whatever. This, instead of using MC delta T, you would use, if it was some percent of alcohol, so like when they say that it's by volume, I assume
30%.
30% by,
It says 30% alcohol.
Instead of the water, which was 50 grams.
It says
So
60 proof whiskey, which is 30% alcohol.
right. So 30% of the volume?
Well, it says there's 50 grams of
Oh,
water.
50 grams. Oh, okay. I would just, okay, you could probably just use by mass then.
Okay.
Because it'd be really annoying if you had to look up the density of alcohol.
It's true.
If you assume it's similar to water, which it kind of is, it's similar, then you could just assume it's by mass. Anyway, whatever. I'll just do it by mass, it's fine. But then you'd have M water, C water, delta T, which I'm not going to write for a second, plus M alcohol, C alcohol. And all this whole thing is delta T. Right? So it's just the heat of them combined. And because they have the same temperature all the time, we can factor that out. They don't have the same mass, obviously, and they don't have the same specific heat. That's the whole point.
So negative Q ice plus ML.
Plus ML, yeah, it's just the thing I just wrote that I erased. But
Thank you.
so in other words, just saying all the heat of the water is absorbed by the ice, plus the leftover heat is also absorbed by the ice into melting, which is this part. All we're doing for the second part is replacing the heat of the water with, instead of this was what we had, MC delta T, we're just adding, we're saying it's M mass of the water times C of the water plus mass of the alcohol times C of the alcohol. Now, this M water is not going to be 50 grams or whatever anymore. It's going to be, 60% of that or whatever it said.
45 grams. No, I'm sorry, 35 grams. Right? 35? Is that wrong?
No, I don't think so.
You guys to do that.
I don't think it's a nice number.
It's not.
Wait, 60?
30.
30%.
50% of 50. Right. Well, 30% of 50 is 15.
Oh, yeah, you're right. Sorry. Yes.
15 to
Thank you.
35. Okay.
Yes. Sorry. Yeah, 35 grams. And then this is going to be 15 grams here. And then these are going to be very different, I think.
Thought I knew my books.
Yeah. So anyway, yeah. So that's the only change in here. It would just be to the side. So the other one I was thinking of was, so you have like a power. The units of power are joules per second, which is a watt. And they're asking you about the time. Now, if they're asking you a question, if they're giving you this, they're saying there's a constant power, and they're asking you how much time does it take to do something. They're really asking you how much energy does it take, right? Because you can just easily compute from energy to time if there's a constant power, right? So there's a first stage is you have ice at let's say negative 10 Kelvin, 10 degrees Celsius. I'm just making this up. I know it's probably not this, but then it goes to ice. So basically, the question they're asking is how long does it take till you get water at 20 degrees Celsius. I'm just making up an example, and they tell you the mass at the beginning. So the mass is going to be the same because nothing about this is going to change the mass. So they're asking, how long does it take to do this? So you have to think of this in many stages, right? The first stage is going to be the ice getting to its melting point. Then it's going to melt. And then it's going to warm up. So we have to think of it like this because getting ice from one temperature to another or getting water from one temperature to another is just fine. We would just use mc delta T. This is how much heat is required. Okay, and we have to use C ice here, and we have to use C water here, and that's fair enough. That's just how you raise temperatures of things. But in between here, of course, we can get to 0 degrees to get ice at 0 degrees Celsius. We can get to water at 0 degrees Celsius, but to get between them, it's not just like it instantly. That's the latent heat, exactly. So this is going to be L. Sorry, it's going to be L, which is the mass times the actual latent heat. Well, I guess, sorry, it's still Q. It's still the heat. But it's M times L. L fusion of water, and it's the same M as the whole time. And so now using this, of course, you're given M. You can look up C ice, C water, and L fusion of ice into water.
Give us C, I think, of water. No,
Yeah.
Water. So specific heat of ice.
of ice, they give us, and they give us T. You were right at negative 10.
It is? Oh, nice. It's not 20, though, is it?
10.
10
Oh, 10 again?
Yeah.
It's boring. I'll leave it 20. Then, of course, you should be able to look up L. If they don't give it to you, you have to look it up. There's
They
no.
don't give it to us. Yeah.
Okay. You look up L, latent heat of fusion for water.
Is
Obviously,
it given in the chapter or something?
it better be.
Okay, that's.
I mean, I'm sure, because I'm like, this is like all the problems when you use water. Because most other things don't freeze or melt at a normal temperature we know of, so. I mean, but anyway, they have to give you this because there's some heat here. And now, of course, now we have that the Q total, the total heat, is just going to be, well, I mean, I guess Q1, Q2, Q3, right? That's the total heat. And then this Q is always in joules, of course. And if you have the amount of heat you need in joules, and you have like however many joules per second it takes, then you could find how many seconds it takes.
Okay.
This is kind of like all the problems are going to be like this. Well, I don't know if that's true, but if that's true, but it's like, this is like the standard problem.
I feel like we've done
Because-
this in an AP physics class.
Yeah, exactly. Yeah.
Do this till thermo.
I didn't take
I think it does in like some kind of chemistry,
in my
AP Chem or something.
senior year of high school AP physics class. I think
There you go.
That's as much physics as
What if they wanted you to say you have ice at -10? What about when it boils?
oh, then you have to do that.
Then we have to do another one. It's not any more complicated. It's just that if they just say, I'm giving it ice and I want to see, when it's vapor,
Would you bring it like the water up to 100?
you would have, right. So this is where they would never mention water in this, because why would, they would just say, I have a mass of ice, this much mass at -10 degrees. When is it steam at, you could just say how much time does it take until it's all vapor. Yeah, I don't want to say steam just because someone told me that I shouldn't say that before. Because it's like, steam is like, this is just a definition thing. But like, technically, okay, I'll take a sidebar for this for a second. Water vapor is invisible, right? Someone knocking?
No, he just.
Oh, okay. Water vapor, actual water vapor is invisible. There's water vapor in the air, right? When it's humid, it's not like you can't see or something. So water vapor is completely invisible. If you can see, like white mist in the air. If you can see something in the air, that's liquid water, right? So like clouds are made of little actual droplets of water, right? Or ice sometimes. Like when something's boiling and you see the steam, that's like liquid water, right?
Got it.
So people use that to mean steam, like the visible component.
Okay.
I like the word steam because ice and water are one word and steam is one word. That's kind of a nice thing. But I've been told that confuses people.
Just say vapor.
So you're supposed to say water vapor. Because vapor also just is anything. Anyway, it's really annoying. I wish there was just a nice word there for it. But anyway, so I'll just call this water vapor. Okay. Well, let's just say if they just said how you take a mass of minus 10 degrees Celsius mass of ice, when is it water vapor? We don't actually need to do any further heating because we know as soon as it's at, this is the lowest temperature you can have water vapor, right? But as soon as it's at this temperature, we're done. So we just need to include another fourth component, which is going to be ML vaporization, right?
Vapor.
Latent heat, yeah. Hashtag LVape. So, anyway. And then, so, we have 2 more. And if we wanted to heat this up, we could do MC delta T, and we could heat it up to, 200 degrees Celsius. Or whatever we want. As high as we want, and it would just be mass again. It's the same mass. C is going to be very different, obviously.
Yeah.
Delta T is the same. So.
Is that considered superheated, or does superheated take into account pressure?
No. Sorry, what is the second thing you said?
Does something that's superheated take into account pressure change?
Yes, this is not superheated.
Okay, thank you.
Superheated means it's
I forget.
at a different temperature in the wrong phase.
Okay.
This is
so
at the
that
right
Okay, that
phase.
is okay.
So it does depend on, yeah.
Yeah.
I mean, well, okay. So,
It'd be like 110, but it's still water.
Yes.
yes. Now, okay, here's the thing though. So I don't know about, so there's 2 things that I think of when I think of superheated, and I don't know if they're the same. Maybe you can tell me. One of them is like the thing where you microwave a thing, and it doesn't, you microwave like water, and it doesn't do anything, and you put a spoon in it, and it's like explodes. Have you heard of that?
No.
That's like a thing where you get water past its boiling point, but there's no like nucleation sites.
Mm.
Like a nucleation site is where it's like a tiny hole where water can turn into a vapor. Like it kind of needs to become a sphere essentially. And if the glass you put in is too sort of symmetric and too smooth, you can just have it not find any sort. Like it doesn't have any sort of
Voids.
nooks and crannies,
Okay,
so to speak. Not a huge fan of the word crannies. I think it sounds weird,
Nooks.
but nooks. Let's just leave it at nooks. to vaporize water in. And if it's too smooth, you can get to where like any impurity you put in it, it will immediately. It's that's what people say is happening when you put the thing from like 2005 or whatever, when you put Mentos. When you put Mentos in Coke, whatever. That's that stupid thing from a long time ago. When you put those in, Coke, obviously it's carbonated, right? And the bottle is pretty smooth. And obviously if you pour it, you're churning it all up, and then it creates all these ripples and currents and stuff. And each of those is a little place where you can make a bubble. But if you just let it sit, it doesn't make all those bubbles, because the bubbles don't really have any sort of reason to, like, there's no places for them to like nucleate essentially. And they don't particularly want to. It's just that if there was like a little tiny hole, they would just turn into gas there. But if you put in one of the Mentos things, they're like rough, like on a really small scale, not like microscopic, but like really small. They're like a little bit rough. And so all of that provides, 1 million or whatever little sites for the bubbles. And they just happen to be at the right size where the bubbles form very quickly. And as soon as it makes a bubble and then the bubble leaves, there's the hole again. So it makes another bubble. So it's like really, really fast. What was I talking about? Okay. Superheating, yeah. So that's like a so CO2 compressed into soda. That's what soda is. Like dissolved CO2. I mean, there's some kind of sense in which it's super saturated. In the sense that if you give it a place to come out, it will leave. Like, it prefers to be in the atmosphere. But it doesn't just go out on its own because it doesn't want to that bad. So that's one sense of superheated. The other sense of superheated, which I think what you're talking about, is if you actually increase the pressure. Yeah, if you increase the pressure of water, you raise the boiling point. So you can have water at 107 degrees that is still liquid water, but it's not boiling yet, right? So you could call that superheated, because then if you just turn the pressure back to normal, it'll instantly boil.
Yeah.
So that is also, I guess, in some sense, it's useful to talk about that as superheated. I wouldn't call that sort of really superheated, because in the context of the pressure being higher, it actually is just at the normal. Its boiling point is actually increased. It's not like a fake, thing. It's literally actually not boiling. It's literally liquid water, right? And the same thing with, I guess this is kind of a stupid example, but like when you put salt on the road, the water doesn't melt. It needs to be a lot colder to freeze water when it has salt in it. So it's like, that's just literally making it different.
That's why you put salt in boiling water. Like lower the boiling point of water so that it boils faster.
It does?
When you make.
I knew you do that. I didn't know why.
It's to lower the boiling
Oh,
point
okay.
of water.
Well, there you go. Yeah, sure. And yeah, and at like high altitudes, they have different recipes sometimes because it boils slower. Yeah. So
that's what I was gonna ask next. That isn't boiling point of water slightly lower at elevation?
Yes.
Yeah.
Which is lower pressure.
Yes.
Right. So yeah. So if you draw the phase diagram, there's like a P versus T. This thing. And I think I tried to draw this in another video, and I sort of didn't really know what I was doing. Not that I know now. But there's something where it's like
It's linear.
this, maybe?
Yeah, okay, I remember that.
Do you know what this is? Okay. And this is like ice. This is water.
My God, yes.
And this is water vapor.
Yes.
Is that how you spell vapor? No,
Vapor.
vapor. And this is the triple point,
Right.
where all three can exist. This goes on forever. This does end, and this is called what is it called? I forgot.
I remember seeing this.
It's the-
saturation point.
No, there's like it's a cool name, but sounds like it means something really cool, but it's not that cool. Anyway, it doesn't really matter. It's the point where the energies are so high, like the temperature is so high, that the difference between a gas that's
Critical point.
critical point.
Critical
That's
point,
it.
thank
Yeah.
you.
This is called the critical point. This is the triple point.
That is a pretty cool name.
Yeah, it sounds really cool, but it's not like it ends up being sort of But it's just basically the point where the energy is so high that so the thing that makes something a liquid versus a gas is the liquid has a bunch of intermolecular bonds that make it sort of a finite volume, right? If you put it in a container as a finite volume, gases will expand to fill any container. So that's one main difference, right? This has like it doesn't have a shape. Neither of them have a shape, right? Solids do, but it feels like second grade or something. These don't have a shape. Solids have a but anyway, no. But the point is that liquids have a finite volume and have intermolecular forces that keep them in the same volume, right? Why doesn't water expand to fill any container? It's because the molecular forces hold them together. But at a certain temperature, they're being energized so much that the intermolecular forces are like comparable to these random fluctuations. So effectively, it's like they're not even really held together at all, right? They are still, because they do have those molecular forces, but they're so energetic that you sort of couldn't tell if you sort of looked at the molecules. You wouldn't be able to tell that they were really had a finite, that they were held together at all, and they would basically fill up any container, even though there are the same strength intermolecular forces. It's just that the temperature is so high that the equidistant theorem, if you put them all in the buckets of the linear motion and rotational motion, those are so high that the intermolecular forces don't. It's sort of hard to tell that they have them, and so above that point, you can't even say that something's a liquid or a gas anymore. It's sort of all the same. It's all the same thing. The energy is higher than, because the intermolecular forces have a finite amount. They don't go on to infinity. There's a finite amount of them, and of course, normally we're in the range where they're much stronger than temperature fluctuations. So water will just sit in the same cup and won't do anything crazy. But if you go up here, you'll get where you could just take out the intermolecular forces and it wouldn't be any different. So that's why above this point, and the actual definition of the point of what does it actually mean, it's probably where this is the temperature at which the average thermal fluctuation, so the average equidistant theorem bucket you put in, is equal to the average intermolecular force. I'm literally making that up. I don't know if that's true, but that sounds like it would be right.
Okay.
Because that's above that point, I actually don't even know what you mean by a liquid anymore. Because you might say that a liquid is defined as a thing that's intermolecular forces are higher than the temperature fluctuations. Anyway, so that would be the critical point. All of that is stuff that no one's talked about in this book yet, so I don't know if it even matters. It might be in the next section. But the point is that ice is here, this is solids, this is liquid. Almost every material has this line here, which is the freezing point line, goes like this. Right? They all have a positive slope. This one has a sort of a negative slope. It's inverse. And it's related to, in a way that I'm not going to be able to explain very well, but it's related somewhat way to the fact that ice takes up more space, has a lower density than water. So when you freeze water, it expands. Right? That's sort of unusual. Most things get smaller, are smallest when they're a solid, they're a little bigger when they're liquid, right? And they're sort of have no size when they're a gas. They're literally as big as you want them. So yeah, most things because when you put them in a solid, they actually have a crystal structure, and almost every time a crystal structure is like a tightly packed repeating pattern. I mean, it's always a repeating pattern, but it's kind of a tightly packed pattern. And then when you allow it to be a liquid and have loose connections, it kind of spreads out. But for some reason, ice, because it makes these weird hexagon things, right? And it just happens to be that structure takes up a lot of space. And it actually happens to take up more space than the water is by itself. So that's why there's this weird line, and I forgot why I was talking about this. Doesn't matter.
You were saying ice expands water expands when it freezes.
Yeah.
It's compressed.
I was talking about superheated things. Yes.
Yes. Well, way back. Okay. Yes. Okay.
Right. So
Wow, we
there's
got
some
this
sense in which you can, if you compress water, I think it's what was I trying to say? I was trying to give some example where you can compress water to a high enough pressure where it will never. I think it's like
There's no room for it to.
this.
Where it meets, it almost meets. Does it ever meet?
I don't know,
Plane? Yeah.
but I think what I mean is that there's some pressure where it couldn't be ice because there's literally not enough room.
Yeah.
It would need to push back.
That's why
Like imagine freezing water. If you this is like a thing. You're not supposed to put water in sealed containers in the freezer.
Mm-hmm.
I saw that.
Why would anyone
and
do
then
that?
you
But
pour it out and it'll.
yeah, or that too. That would be super cool. Yeah.
Yeah.
Because yes. Oh, okay. That's a better thing than what I was gonna say.
Heck yeah.
That wasn't what I was gonna say, but that's better. Where you take something, you put it in the freezer in a sealed container, and I guess the pressure is enough that it doesn't I guess if you leave it long enough, it
I
might
think
freeze.
it's like
but
a Poland Spring bottle that has not been opened or something like that.
I've
Cold
seen
Spring
that.
bottle's not been opened,
And then
Okay.
you take it out and you pour it, and it'll turn into ice. and
yes,
you pour
because
it.
those molecules are liquid water because they literally don't have enough space to make the crystal structure of ice.
Mhm.
And there's no other. This is all they can make. I mean, there's other crystal structures of water that you could make in like. You can look it up. There's a thing if you want to look these up. These are you don't need to look this up. But there's a thing called like Ice 4, which is like a really funny name for a sounds like a movie or something. Anyway, there's a thing called Ice 4 and Ice 5 and Ice 6 and Ice 1 I believe is just the normal crystal structure. But you can draw these diagrams of crystals, and there's different configurations that water can be in. It can only be in there's other phase diagrams where it's like if it's here it's Ice 6. Like they're ridiculously like you never see them on Earth. But just people were saying like on Europa or like these moons of
Yeah.
planets or like really planets that are just literally made of water, like in other solar systems or whatever. They actually can be made of different crystal structures of ice. Anyway, the point is that the only one we see is this one that happens to take up more. Actually, the reason we see these is because there's some like Europa, like the moon of Jupiter, I think it is. It's literally like all ice and it's freezing. There's no heat. I mean, it's so far away from the sun that it's but it's so much pressure because it's like a planet full. It's like filled with water that there's enough pressure that it's like super cooled, but it's beyond super cooled water to where it'll be like, all right, fine, I'll be a solid, like chill, like you don't need to, and it'll be a solid in like this ridiculously weird configuration that only exists if it's like you really have to crush it, So like sort of it's just like up here it has to be that. So so what I was saying is of course in normal circumstances in like the freezer with Poland Spring.
Cyclohexane rings.
Yeah, if you what was that?
Cyclohexane rings. Is that what they make?
I don't know. Probably. You would if you read the article you might be able to explain it to me.
Google it real quick.
But there's a Wikipedia page for phases
No,
of
just
ice,
mean
I
like
think.
in the freezer.
Oh, in the freezer, I don't know. I assume in the freezer it's just super cooled water. And because
okay, yeah, no, I got what you're saying.
because they can't make the ice crystals, they're not going to make anything else because they're not high enough pressure. But then, of course, when you open it, well, they're still colder than freezing. And so once you relieve the pressure and they have room to expand, they're like, oh, thank God, I can freeze. And as soon as one of them line, and I know this is not accurate, but as soon as like one of them, I drew it the other way the other time, but like starts to line up, they start to make the hexagons or whatever it is. And again, I know this is not accurate, but
You're close.
yes. Anyway, let's just erase this. So then once it starts, they can spread, and this happens in a lot of things like anyway, whatever. There's other I can't think of what it is, but there's some example that you can actually do that's like some material that when you shake. Actually, there's one that's I think it's how like heating things work, like if you those like toe heating
Oh,
pads or
Foot warmers?
yeah.
foot warmers or
Yeah.
like hot packs. Why
Yeah.
am I having such a hard time? Those things are usually where, I mean, it's usually just sometimes it's just two
They have
chemicals
these
that
really
mix.
cool ones where you like snap the middle button. And
Yeah.
it expands.
That's
and they're
that's what I
reusable.
was gonna say. Yes, the ones where you snap it and you literally see it like crystallize.
Yeah.
That's because there's
so
one crystal structure that's sort of it's not unstable. It's perfectly stable. It's just that it prefers to be another crystal structure. It's just that it's not given any there's no reason for it to do that. It's sort of like if you plotted the energy, you might have like this. So this is one place where the energy is,
Mhm.
and it's totally fine here. It's not it's not unstable. Unstable would be like here. That's unstable. But here is stable. But if you crack it in the middle and you give it like a bunch of energy in one place,
Oh.
one piece of it's going to kind of jump and be like, oh, I really like to be down here. And then it's going to kind of pull the next, so they're all connected. So it's going to kind
Chain
of pull the
reaction.
next.
Yeah.
It's a chain reaction, and you can literally see it.
Yep.
And because
Super cool looking.
it dropped energy,
Mhm.
this is some amount of heat that got released.
Oh,
So this
yeah.
is releasing heat. That's
They're
why
hot.
it's. Other ones could go the other way.
Yeah, it's this thing.
Yeah.
Exactly. So
Yes, exactly. That's right.
to
Exactly.
get it back to the liquid though, or
You have
the
to
gel
boil it
state,
in
you have to
hot
boil
water.
it. Why? So you're giving it enough heat to get it back up.
You
to
would boil it,
stabilize?
and then somehow you would
Yeah, you have to
make
boil
sure it lands in this one.
and then let it sit for 10 minutes. Or you boil it for 10 minutes and then you just let it sit in the water and then you dump it out when it's cool.
So if you shocked it
Okay.
again, it would go back to it would
I don't know.
react again if you shock.
Yeah.
So taking it out would
I
shock it.
haven't tried
I haven't tried
because
it.
it's hot water.
I'm not
I'll
sure.
bring some in, and you can play with it.
I mean, somehow, the point is that it wants to be in the lowest energy possible. When you boil it, the energy's up here, and it could be in any. I mean, it's not in any of these minima.
Yeah.
Potential minima, but
Really cool.
this is like you actually once you like
So jazzed.
once you think about energy versus something
Can I write this
Actually-
on the test?
states.
No, something is.
No, I would not. Something is good. Once you think about this type of thing, so if you draw, that's why am I drawing it so like weird? It's I just mean, how do I want to draw this? This. Imagine this. Imagine this is like a potential,
Mhm.
or just some energy over. Like you could think of this as literally like gravitational energy, in which case this would be like a mountain, right?
Mhm.
And this is one little hill. Things can be stable. This point is called stable.
Mhm.
This point is called stable. This point is called unstable. There's another thing called metastable, which is not, I'm just drawing this to distinguish. Metastable is like that, where if you push it this way, it'll be like, oh, it's fine. But if you push it the other way, it'll fall. Anyway, that's not what I'm talking about.
No, it's similar to like enzymes facilitating a reaction.
Exactly. I was just going to say, once you see this, so this state here is a totally legitimate vacuum state. It's called, in high energy physics, it would be called a vacuum state. In this, it would be called configuration,
Mhm.
sort of not the lowest energy configuration, but a totally stable configuration. Because stable means if you give it small adjustments, it just rolls back, which is correct, right? But if you give it perturbations to about this size, if you give it enough energy about this size, or if it's at a temperature where the fluctuations in temperature are about this size, or if you snap it and you give it a bunch of energy, it will naturally fall into here. And then if it's connected in another dimension, like if it's, in that case, it's in 3 dimensions, obviously. Then if you bring one of the things over here, one little region, you bring it over here, the neighboring ones are sort of pulled along for the ride, and that's the whole thing. So I'm saying what I was going to say about this is that once you see this picture in something, you realize it's like most of physics is just this picture. Like most of physics is like things being in one vacuum and then being in a better vacuum. And again, if these are not the same, if these are at different energies, by conservation of energy, there's some heat between them. If this is all thermal physics, this is a heat between them. And so that heat gets radiated somehow because this configuration has less potential energy in it. That's how you'd say it. Because you went from some potential energy to some less potential energy, you have now kinetic energy, I guess, gets radiated. But of course, in this world, kinetic energy means heat because the molecules moving. So that's how those warmers work. Now, how the cooling ones work, I have no idea. I assume
that's
it's
just how you cool it down. So like once you snap it and it becomes a solid, it won't change. So you have to put it in boiling water.
Oh yeah, no, I mean there's cold packs,
there
right?
are.
Yeah, there's
Mhm.
yeah, you can buy a cold pack.
Well, I know you can like put them in a freezer, but like I
No,
didn't
no,
know
there's like things you can break a thing and it becomes cold.
Yeah, you can only use it once though.
Oh, I know what you're saying.
Those you can't reset. Yeah.
No.
Okay.
Now how those work, I have no idea. I mean, I know that there's
You have to,
there's endothermic
break
reactions.
the interior bag.
Yeah, I assume that's just a chemical
I
reaction.
think it
There's
is.
So it's
something
not
that-
about this because this is endlessly reusable.
There's like a water pack in it, and you have to actually break it.
Yeah, it's hard.
It
Yeah.
just pulls in all the heat.
Yeah, I mean, you can make up any reaction that's just absorbs heat.
Yeah.
So I guess that's probably how it works.
I thought you meant to cool down.
No, because I was gonna say usually the endothermic ones are very hard to redo to
I don't
undo.
think you can undo it. Yeah.
Yeah, I mean you'd
Once
have
it
to.
goes-
Yeah, no, you can't.
Yeah.
You can't. I know what you're talking about now. Like the ones you get in first aid kits.
Yes.
Yeah,
Yeah, I know what you're talking about now. You can't reuse those.
Right, because
You break something.
it's generally very hard. It's much harder to cool things than heat things.
Yeah.
Because if you mess up heating something by like accidentally giving more energy in a disordered way,
Mhm.
it's still hot. But if you try to cool something, you can't mess up at all because you're trying to get all the energy away.
Right.
So if you mess up and leak some, you're ruining it.
Yes.
So cooling things is generally much. That's why refrigerators and stuff are usually take a lot of energy.
Yeah.
Like anytime we're kind of again getting a little off topic. I mean, I'm getting off topic, I should say.
We're learning.
It's not your fault, but I'm just saying like when you plug in a heater, right?
Electric heater.
Like a space
Space
Yeah,
heater?
like a space heater, electric heater. Yeah, like when you plug an electric heater, it's literally 100% efficient because if there's any waste,
It's heat.
it's heat, and that's what the point is. So it's literally 100% of the energy you're taking out of it, unless it's making a sound. In which case, of
Yes.
course, sound energy is, well, it'll turn into heat, I guess. But unless there's a light on it or something, it's like basically 100% of the energy converted to heat. When you make a fridge or refrigerator, you have to like compress some like Freon, or I mean, it's not Freon anymore. I think it used to be like Freon or whatever it is, and then let it expand so that it cools, and that is not at all 100%. It's very inefficient because you have to move the heat somewhere. So to heat something, you just have to take energy out of the wall and spread it anywhere you can, and that heats up the room.
Mhm.
It doesn't even matter if you're bad at spreading it because it's going to get to the room anyway. There's nowhere else. You can't go back into the wall, right? But when you make a refrigerator, you can't get coldness to come out of the wall. You can only use the wall energy to move heat away from the inside of the fridge.
Like an air conditioner.
Like an air conditioner,
Yes.
exactly what you're doing with an air conditioner and a fridge is just moving heat somewhere else.
Yeah.
So when you put a fridge in somewhere, you're actually, all of the heat is going into your house.
Mm-hmm.
You're actually heating up your house.
Mhm.
I mean, I know everyone knows this, I guess, but well, with air conditioner, it's obvious because one side goes outside.
Right.
It's literally heating up the outside, and then using some special pressure things, you can actually get it to take more heat from the inside. But it takes some non-zero amount of energy just to do the process.
Mhm.
So it's not even like you're efficiently moving the heat, right? You're actually using energy to heat up somewhere else, and it accidentally cools the inside. That's kind of how cooling works. So it's like cooling generally is much, much more difficult. And it's all about the second law of thermodynamics. Oh, I wish I had planned this, because
There you
this
go.
all comes down to, because we talked about the first law.
Yep.
This is all first law
That's
stuff.
what you need us for.
There was no W. And remember, the first law is a W, but there's no W here, but who cares? That's not a big deal. That's just with the pressure and volume, PV equals nRT kind of thing. But the second law is that, yes, thank you, I'm glad you're here. Delta S is greater than 0, and S is entropy.
Yeah.
Exactly. So this means that the change in entropy of any closed system, you have to, of course, have all these caveats like it has to be a closed system, blah, 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 has to be, always increases.
Yes.
Which is kind of, in one sense, it's like really powerful because it's the only thing in physics. It's basically the only thing in all of fundamental physics that is not symmetric in time. So all of the equations of motion that we've talked about, like, roller coasters and energy and projectiles, all of those, nowhere does it say that time has to go forward and it can't go backward. Like, no one cares. Like, put time backward, it's fine. If you shoot a cannon from the ground onto like a cliff, it's exactly the same as if you shoot it. You know what I mean? Everything's reversible. This is not reversible. And so in some sense, it's incredibly like a powerful statement about physics that entropy should increase. It should not decrease, right? It's not like there's not anything, and this usually over time it increases. Well, yeah, it is over time. This delta means over time, but in another sense, it's not that impressive. This is actually why I like this, because in some sense it's really powerful because it's the only thing that's not time invertible that we know of. But in another sense, it's basically like saying if you start with a box of gas, let's just call the gas a bunch of dots, and you line it all up in like a grid, right? And then you let it go, it will turn into, if you just take a random snapshot later, it'll be kind of random, right? And then if you take a random snapshot later, it'll still be random, right? And the point is that it's incredibly unlikely that you'll get to this state again. Or let's just say you started with this, it's very unlikely that you'd go this way. And it's just saying that the entropy is increasing. And the reason I'm saying that's not that impressive of a statement is because, well, yeah, but like, how many states are there that are like perfectly even like this? There's like, well, I guess you could rearrange the molecules and it would look the same. So there's like, 40 states or whatever that would look kind of like this. And how many states are there where they look random? Like a quadrillion. Like an incredibly large number. So if you're just saying that you get a random state, which is, if you effectively say it's a random, then most of the time you're not going to get a nice state. So like, what is this really even saying? It's just saying that like, there's not that many, Yeah, just saying probability. The probability of getting a nice looking state, well, there's a lot less of them. So if it's truly random, which is not really random, but like if we approximate it as being random, you're just very unlikely to get something that's sort of ordered or, like imagine a box with gas in it, but all the gas is like clumped up in the corner. You could very easily start a system like that because by just releasing the gas from the corner. But what are the odds that it will ever go back to the corner? Almost none. But then again, now just go back to how many states, if you just say these are random dots in a random box, the box isn't random, but the dots are random. How many states, if you try to put them in boxes, obviously there's infinitely many, of course, but if you try to like make them finite and put like a very fine grid around it or whatever and count where they are, how many of them have them all in the corner? How many states, how many types of boxes have them all in the corner? Compared to all of them, it's almost zero. So the odds that you'd see it are almost zero, even if you start. So therefore, if you started with it, you'll almost never get back to it. So that's not that impressive of a statement. It's just like, well, sure. You just see the thing that there's most of. Like the odds that you'll see exactly this state is also very low, right? Because every state is equally probable. It's random. But it's just that we call this random, and we call most of them random, and we call very few of them specific, and therefore things tend to get less specific. But it's just because this particular state doesn't seem special to us. So you can think of it in the one sense of like it's this fundamental thing that says that time has this forward direction that has nothing to do with the reverse direction, that things can only go a certain way, and it's very difficult to get them to go back, right? So that seems very fundamental to physics, but there's also this other view of it, which is that it's easy to configure something, but randomly things tend to just be random. And most of the time we don't care enough to care about the difference between these two. We just call them both random. So it's more, so maybe it's like a sense of maybe it's just a statement about what we consider important. We consider this state to have a very low entropy, and we consider most states to have a very high entropy. Well, if the vast majority of states we say have a high entropy, then of course it's just going to increase. Well, yeah, sure. That's just how we're describing it. Anyway, that's the second law of thermodynamics.
That's where cycles come in. Start studying cycles.
Cycles of what?
Rankine cycle. No.
What is that?
Rankine cycle?
Rankine?
It's Rankine. Refrigeration?
You're saying like Ronald
Oh.
Reagan.
No,
Like-
Rankine.
No, I don't know that. I know the Carnot cycle.
Okay, that's another one. That's
Okay.
That's,
These are
yeah, that's the combustion engine. Is that Carnot?
yeah. I don't think anyone actually uses it, but it's like adiabatic.
Oh, no.
There's
it's
like-
not-
'cause
it's not
there-
the gas engine. Though?
There's like PV, and depending on how you go in it, if you make a square, it's called something cycle.
Oh, I know you're
This is a weird one because it's sort of weird to do this, but the Carnot cycle has like these, some of them are adiabatic and some of them are constant temperature or isothermic,
Mhm.
and it's easy to make something isothermic, whatever. It's easy to make something constant temperature because you just don't allow any heat to change.
Diesel cycle, the Otto cycle. That's what I was thinking of.
I see. Okay.
That's what I was thinking. Oh, so we learned that's what Thermo 2 was about,
Oh, okay.
and
Well, these are actually even simpler in some way than those because those
that's
involve.
ideal.
Huh?
That's considered an ideal cycle.
Oh yeah. This. Well, these are for ideal gases, and they're for one gas.
Okay.
If you're talking about like how actual cars work,
Mhm.
of course there's not just one gas. There's ignition. So those actually are probably more complicated. But this one, yeah, is like Carnot.
Yep.
Is a French person. There's a T. That's why
Yep.
it's French. But yeah, this is somehow, I forgot why. It's because it's somehow the most efficient one you could get or something. And it's because some of these lines here, so it goes around like this. Some of these lines are adiabatic, so entropy doesn't change. And some of these lines are isothermal, which means that temperature doesn't change. And for whatever reason, that's really nice. I forgot. But we'll probably see it in like the next chapter.
Mm.
And you can figure out the efficiency, usually eta they call it, the efficiency of this by I forgot what the definition is, but it's somehow the amount of heat you lose is bad for efficiency.
Yeah.
It's very close to 1 sometimes. Anyway,
I just remember the combustion cycle sucks.
Yeah, engines are super
Not efficient.
They get crazy hot.
I think the Rankine cycle was a little, which refrigeration? I think that's
Yeah.
refrigeration is a
Oh,
little
okay.
higher.
Yeah.
Not much though. I remember my thermal professor just continuously said, "Pump rejects the pump rejects heat."
Yeah.
That's all- I remember her saying that.
well, anyway, that's all I have. If you want the actual, so
I'll watch the video. I'm
Yeah.
not gonna make you do the
Not gonna make you do
no,
it
I
again.
mean I don't mind. It's just that some of them are like
that easy.
great, like
like
they're not like they're not really even worth. Like
Yeah.
one of them's like how much energy is in a hurricane, which
Oh, yeah.
I don't know how to answer that.
Yeah.
So I just said that you just take the volume of the hurricane.
Yeah.
So look up, I don't know, the radius. What I don't
Okay.
know how to, and just find it as a volume and
What
just like
size hurricane?
find how much kinetic energy find the average wind speed
Okay.
and just find the kinetic energy of that much air maybe. I don't know. I honestly have no idea what he wants from that question. So whatever you figure out to do, just you can do it that way.
Okay.
You said you went through all of them in the last one.
Yeah. Oh no, not yeah. It's in the
11 is
12
a
or
bear. It's a mile long.
yes.
It's a great
Which was,
time.
what was that one?
In a metal, one might easily ask.
Oh yes,
why
that
don't
was a
free
good one.
electrons in metals contribute to 3/2 kBT?
Yes. Okay, that's I do that in the video.
Okay.
Okay.
I really don't want to do it again.
I don't blame you.
I
No,
literally
yeah,
won't
no.
remember how to do it.
I don't
I
wanna
can
read
tell
it
you
again.
the idea behind it though,
Okay.
if you'd like.
Yeah. I'll
Sure.
listen to it.
Because the idea is actually kind of cool. I will not get the details right now. Even in the video, I seem a little uncertain, which is because I was. But the idea is actually really cool. And I think, again, as usual, the idea is probably, although the quiz didn't seem that much.
Quiz was
Don't even.
murder.
I thought the quiz was going to be a little more qualitative than it was.
Me too.
So you didn't like it?
No.
Nope.
Oh.
Sure
I
is.
kind of liked it. I thought it was kind of nice.
Yeah, because you
Well,
understand
you
all of this.
understand.
And
No,
you're
but
a
like-
genius.
There was I liked the half infinite.
Okay, that I
yeah.
liked. That was
Okay.
fine.
Because
When
you just boundary conditions. You know both of the boundary conditions.
what messed
You just do
me
one of
up
each.
was when he was like, "I don't want letters like A," and
Yeah.
he was like, "I just want ratio," and I was like, "I'm just handing this goddamn thing. I don't know what you want from me."
It's because remember the thing where you got tangent of.
I
I
had
don't know if you
that.
want to hear the answer.
No, I had that. Like the
Tangent
Z
of LA equals
Z over.
or whatever it was.
It's like,
This has no. He meant
Wow, I can't wait to see that grade.
Oh,
like-
okay. Maybe you were
was
because
it like Z over ZO minus 1?
yeah.
I had
Oh
that.
yeah. No, that's fine.
Oh.
That's correct.
Oh.
He meant that he didn't want like you know how
I had that for the.
he doesn't want
Oh.
this A.
Okay.
So when you solve the Schrodinger equation, you
It-
always get
Aren't
these
those boundaries
coefficients.
1 and 2 though, or bound 1 and 3, and then 2 was the tan.
It was this question, right?
Yeah.
It was well here it's 0. In 2 and 3 you get this boundary condition.
Right.
And in 2, if you just said what's the Schrodinger equation in 2 and 3,
Mhm.
you have to put these things, these
Mhm.
coefficients A plus. I mean, so in 2 it would be I can use cosine and sine. You don't have to use cosine and sine, but I will for now. And then so this is psi 2,
Right.
and psi 3 is and the energy was here, right?
Yeah.
Psi 3 was just it was like e to the minus kx or whatever times c. So I think he meant if you just say that at x equals a, and you just plug, sorry, this is x. So these are the actual answers for psi 2 and psi 3, okay? The fact that there's a boundary condition means that if you just plugged in a to all of these and wrote that they're equal and then left it, he meant that that's not completely
Okay.
done. Because, of course, that's true, but you didn't simplify it enough. Because the second one is that the derivatives
Okay.
at a have to equal, and once you set the derivatives equal, then you can do the canceling, and you get like tan of ka equals whatever the other side was.
Yeah.
Anyway, you end up getting that there's no capital A, B, and C are not in this statement.
Right. It was like Z over ZO minus 1.
Yeah,
So
yeah,
Z
yeah.
was like LA, and the other one was
Yeah.
the square root of something over.
Right. You didn't even need to go that far though. You could have left it with the tan. I mean, I'm glad you. But if you left it with tan of Ka equals, I think it was just Ka, or no, K prime, because this is a different K. But if you, this is the statement he wanted. There's no capital A, B, or capital C in here. That's what he meant.
I'm gonna find what I
Yeah,
wrote
because
down.
when he first said that, I was
Tell me
like,
whether
I was literally
this
was
is
like,
accurate.
did he mean to say that? Like, I don't think that's right because, like,
I
how could you
wrote
possibly solve? Like, if he doesn't want you to solve it, then
the tan of z equals zo over z squared minus 1.
yeah,
Where
that's
z equals la and zo
Yeah.
equals a over h bar square root of 2 mvo.
Great.
Is that good?
is that what you wrote?
Yes.
Oh, that's probably fine.
Okay.
Because if you just wrote this comes from dividing, setting this equal to this
Mhm.
with a's, and then dividing it by when you do the derivative,
Okay.
and you get
Just lost. Oh my gosh.
yeah, and you get that the a's. Oh, actually, sorry, you can't even have cosine because it has to go to 0 here. So it's actually this, because the cosine wouldn't be 0 at x equals 0. So it's b and c, or whatever. You could have used any letters, but he just meant he doesn't want you to leave b and c because that means you didn't plug in both boundary conditions. Because if you do plug in both, you can do some division and divide sine by cosine, which is going to be in the derivative of psi 2, and then you can get tan and this, and there's no, the b's cancel and the c's cancel actually.
Just okay, there you go. Yeah.
Something like this. I'll put approximately because I don't know if that's right. It's right.
Tan of la equals k over l.
Oh, yeah, that's probably right. So, like that. And there's no A, I don't think.
I could see, yeah.
Like
K
that.
over
Yeah.
A.
So anyway, the point is that this has none of these in it.
Okay.
That's
okay.
what he meant.
Then I feel a little bit better
Yeah, yeah.
because he said no letters and I was like, boy.
No, yeah, he just
what are
meant
you
no,
talking about?
no overall constants.
Okay, that's all
Which
right. I
is-
put the tan down. I remember
Yeah,
specifically.
yeah. No,
put
if
the
you have
tan
if you have
down.
tan somewhere, you'll probably get it right.
Okay. All right. I need one.
I think it's tan at least.
One. The rest are wrong. So one right is good.
Yeah.
What was that Meatloaf song? 2 out of 3 ain't bad.
Well, 1 out of 5.
1 out of 5. It's not. It's okay.
Okay. Anyway,
But I was going to talk about the
the idea behind the lemon.
the idea behind the temperature. So the point is that, remember how we had the bands, right? When the last time, in an actual material, you have these 3 kx, ky, and kz are these 3 axes of k values you can have. So this is just in a 3D material, like in a metal or whatever. All your electrons are in these states, and when you start filling them up, and you just want to say that there's a bunch of electrons in these states, then you can start filling them up in the middle, and the middle means k is like the low values of the k, so it's like momentum, and you start filling them up such that they form, it's called the Fermi sphere. Pretend this is filled up. So this is called the Fermi sphere. And the Fermi sphere has a radius, k. Actually, can I see the question again?
It's supposed to be America.
Radius kf, I guess. I guess a little underwhelming. And then E, the energy is going to be h bar squared kf squared over 2m. Okay. Okay. I guess I have less to say than I thought. Oh yeah, good. They say it. Okay, good. So here we go. So so this is this is like a metal again. Every electron has a certain value of kx, ky, kz. It's just like there's bands, but it's in 3 dimensions now. Don't worry about don't try to imagine what these are. It's impossible. Don't even. It's really hard. Just know that this describes all the electrons in some metal, some object, let's say. And the sphere of all of them, because it's called the Fermi sphere, because they are sort of packed into the center and sort of expand as you put more electrons in them. What they're asking about here is that if you consider this as a gas of electrons and you say that this metal or whatever material this is gets some energy, if all the electrons got that energy and sort of it's like the equipartition theorem. If every electron here got 1/2 kT, or sorry, 3/2 kT, I guess, because they can have 3, right? Then how much would the temperature raise, right? It's kind of like when you try to compute the specific heat. You look at all the possible places with the energy. If there's n electrons, let's just say there's n electrons, then there's n times 3/2 kT places with the energy. So that would be fine. The problem, the question on the homework is about how that's actually not how it really works, because the energy if you're at a certain temperature, some of the electrons, let's say the ones in the middle, can't actually, remember this is the Fermi sphere, they're actually packed completely into their states. They can't move really at all because every state next to them is occupied, so they can't be in the same state. So if you actually give energy to ones in the middle, they can't really do anything. So if you give one to the ones on the outside, they could do stuff, they could start moving around and stuff. And so the question is about how only electrons within a certain range of the edge of the Fermi sphere, right? So a certain range of energies, a certain range of Ks, and I think they say it's within KT, so within KT of Fermi sphere, get thermally excited. So this is get thermally excited. So that means that it's not n electrons that all have 3/2 kT or whatever degrees of freedom. It's actually only some on the outer shell of the Fermi sphere. So effectively, this material at some temperature T, this acts like a gas of electrons with only some fraction of all the electrons. And the question, I think that the sort of whole point of this question is, what percent? They're asking literally what percent of electrons are, I'll say, thermal. I don't know, I forgot the language they use, but what they mean is thermal, which just means act like particles of a gas. Right? The ones in the middle are not thermal because they don't have the equipartition theorem applied to them. If you raise their temperature, they sort of don't want the temperature. The energy, they just sort of they can't do anything with because they can't be excited, they can't move. Mm-hmm. So they just sort of would give up the energy to the outer ones. So effectively, what percent is the question? Electrons are thermal, and they tell you that if their energy is within kT of the Fermi sphere, so in other words, if their energy is within kT of this edge here, they will get excited, right? And so of course you can see that if T is really big, eventually the whole thing will get excited. So if the temperature is hot enough, like in the sun, mm-hmm. There's no such thing. They'll never be compact in a sphere. They'll always be moving all the time. But if it's room temperature, I think they ask specifically for room temperature. So at 300 Kelvin, what is the percent of electrons? That's what you have to compute. And again, look at the other video for all the calculations. I'm not going to be able to reproduce them perfectly. But effectively, you have to find if this is the energy of the electron in this Kf, mm-hmm. what we're looking for is electrons with energy kBt. Electrons with energy h bar squared k f squared over 2m. This is just the maximum energy at the edge, minus kBt. That's the lowest energy electron. That's the electron right here. And to find the K, we can always use this formula. E is always, we can actually rearrange this, 2me over h bar, square root of this is K. This is always true. This is I used for specifically the F value, the highest one, but this is always true. So we can take this energy and like square root, it's gonna look really stupid, but we can take 2me square root over h bar, and this is the K value of this electron down here, right? And what we want to find is actually the volume of this shell, right, this shaded shell, because those are the ones that are going to participate, right? It's going to be all of the electrons that are outside of this inner shell. This inner shell is given by this energy, which is given by this K. So I'll call this K inner. And K outer is going to be like the Kf, the Fermi energy. All the electrons within this shell here are going to be the percent, is going to be the, basically if we find the volume of the whole thing and then the volume of the inner shell and we subtract them, we'll get the volume of this. And once we have the volume of this, we can divide it by the total volume and get the percent of the volume that this shell is. So, and that will be, of course, because the electrons are evenly distributed. It's like exactly, then we can just take that percent and that would be the percent of the electrons. So the percent of the electrons is going to be the same as the percent of volume of, I'll call it the thermal shell. And this shell here is the thermal shell. And the reason we knew what that was is because they told us the thermal shell has, essentially it has a thickness kBt. Right? And it's kBt from the outside, because the outside ones can definitely be excited. So down to thickness kBt, it's a little confusing because kb is a constant, and this k is a value, is like a position vector kind of thing. So it's a little confusing. kb is literally a number, which is not, it's both of those constant. Anyway, this is Fermi, the Fermi level, the Fermi momentum. This is the, wave vector value. Anyway. But the point is that, yeah, that's the spirit of this problem. And the calculations are done in the, hopefully correctly, in the other, yeah. Yes, I'm pretty sure they're done correctly. So I know this doesn't inspire confidence, but one of the things you need to use is the volume of a sphere in 3 dimensions. So we know the radius of the inner one is K inner. The radius of the outer one is Kf. Right? That's so in other words, let's draw like a cross section. So here's K equals 0. This radius is K inner. This radius is Kf, and therefore the difference between them is K radical 2m kBt over h bar. Right, because that's how you go from an energy. If the energy sort of penetrates to this depth, then the K penetrates to this much. That's just the relation between them. Therefore, we have to use the volume of this minus the volume of this, and the volume of the sphere is given by 4/3 pi r cubed is the volume of the sphere, and so we have to do things where we cube like this equation. So it's a little annoying looking. Yeah, I know. So we get things with like the powers of 3/2 and 2/3 and stuff.
So it's going to be taking that equation and taking the other K equation on the upper right corner and just plugging both of those values in for the volume of the sphere and then subtracting them. And that's all we got to do.
Yeah, so yes, exactly. Yeah. Yep. That's basically it.
Wow.
But I would watch the video because there may be some other subtlety that I mentioned in there. I mean, that's effectively what we're doing.
Okay.
Yeah. And the answer, I believe, so I'll just tell you the answer. I don't remember what it is, but I think it's like less than 1%.
Okay.
So that's just an interesting, first of all, interesting for 2 ways. One, if you do this and you get 50%, it's probably wrong. Which could mean that what I just said I forgot something. But in the video, I believe it should be right. And secondly, that's an interesting, let's think about what that means. That means that the only electrons that behave like a gas, like get excited when you put energy into them, that raise their temperature in a metal at 300 Kelvin, right? So sorry, this 300 Kelvin is this T here, right? Because that's the only ones that are at 300 Kelvin that get excited are like less than 1% of all the electrons in a material. So it's sort of like the thing with the bands. It's like you imagine the bands and like a band that's partially full. Well, how many of them get sort of move around in the conduction layer? It's like imagine if only like the top two actually did anything. I guess you might be like, well, as long as it's conductive, then who cares? Which fair enough. But it's kind of interesting that like you kind of imagine all of them, or at least most of them, would get involved. But on the other hand, T equals 300 Kelvin is actually kind of small. Like in the sun, it's way hotter. So in the sun, you can imagine what if you take T to be really, really hot? That would mean that your K inner would be smaller, right? Because this number is bigger. So K inner would be smaller and smaller and smaller. And eventually, if T is so hot, then the energy within kBT of the Fermi sphere would be like the whole thing. So your K inner would be like this, and so this region would be your thermal layer. I mean, I guess T could be higher than the other one. T could be higher than your whole thing. In that case, your whole thing would become thermal, and it would essentially be like a free gas, which is definitely what happens in the sun because there is no atoms even in the sun because everything is the plasma, right? The electrons are completely free, and it's basically just another way you could say that is because the bonds between an electron and a proton, which both exist in the sun, are so small. The energy is so small compared to the thermal energies that these, the kinetic energy, the average kinetic energy they have if you use the equidistant theorem of the temperature of the sun and figure out the average velocity of an electron and the average like kinetic energy in the x direction of an electron, for example, it would be much, much, much higher than the potential energy of a hydrogen atom. Right? We did things with the 13.6 electron volts, right? Is like the n equals 1 state of a hydrogen atom. You would find that the average like kinetic energy of an electron in the sun is so much bigger than that it would just never be in an atom, right? It couldn't have, it has too much energy. And so that's why there's no atoms in the sun. I mean, we say the sun is made of helium, hydrogen, but of course it's just made of the nuclei. And actually, there was another thing that Charlie asked in class that I wanted to answer, but I didn't want to be annoying about it, but I'll answer it now because can't be annoying now. Where he was asking, where does the energy of the sun come from? Because he asked, Professor Z asked, where does the energy of the hurricane come from? Mm-hmm. And I had absolutely no idea what he wanted as the answer. So I was literally being like, I don't even know what he's. I think he meant the sun, which is fair enough. That's a good answer. So anyway, whatever. I didn't know if he meant like heat of vaporization or anyway. So what it actually comes from, if you want to know, again, this has nothing to do with the class, but it comes from the sun is mostly made of hydrogen, right? And don't worry about neutrons and protons too much. They could easily be switched. It's so hot in the sun that you could have all these reactions where they emit positrons and electrons and they conserve charge. It's fine. So basically, imagine it's composed of 4 protons, and then a couple of them somehow in the process turn into neutrons. That's fine. And then they combine and they make, these are zeros. They make, this is a helium nucleus, right? So 2 protons, 2 neutrons. The mass of this, if you actually take the mass, this is not the mass of the whole atom, but just the mass of a helium nucleus is slightly less than 4 times the mass of a hydrogen nucleus. Even if you care about the fact that neutrons are slightly heavier than protons, which is like not that much, but even if you add that up, it's slightly less than the mass. So where does the mass go, right? Like what happens to it? Well, it just gets emitted, and that's where this mass goes. So the extra mass goes into this M, and through this equation, you can find out how much energy is released. So it releases in the form of photons. But the slight difference in mass between the helium that the sun produces and the hydrogen that it's made of goes through this equation. C squared is a very large number, obviously. And so the energy released is very big. Anyway, if these weighed exactly the same, the sun would not release any energy. And helium is named after the sun, right? Helios. God of the sun. It was discovered on the sun before it was discovered on Earth.
Oh.
I mean, not you didn't go there, but
No, but
they
No
used spectroscopy, and they knew that if you look at the spectrum of the energy levels for, well, they knew hydrogen, they knew oxygen, they knew nitrogen, and when you look at it in the sky during the day, you see a bunch of stuff. I assume you see like nitrogen, oxygen, and that kind of stuff, and they plot them all out, and they were like, there's these like 3 bands or so in the visible spectrum that we don't know what they're from. They're from some element, and we only see them on things that are from sunlight, and we don't see them from from other light sources. I don't know what other natural light sources were there in like 1600, but like fire, we don't see them from like fire. It's fire. Or from burning things. I mean, you could light things on fire and measure the spectrum. You could see, neon. They probably knew about, I guess. Actually, they probably didn't know about neon. But anyway, the point is that you can see all these different things, and they could see all the elements. And they found an element that seemed to be only on the sun and never anywhere else, because it had these bands that you'd only see from sunlight. And so they just named it after the sun. They were like, it must be made of some helium. It's like some element that the sun is made of. And then they realized, oh, there's helium all over the place. Actually, most of the helium we get on Earth to make like party balloons comes from the radioactive decay of uranium and stuff in the Earth, because when it decays, there's a thing called alpha decay, right, which is where it emits literally a helium nucleus. And those things, of course, in the sun, they just fly off and who cares. But on Earth, that's like a charged particle, so they tend to not want to be charged. They just get electrons, and then you just call it helium, because it is helium, but it came from sort of an alpha particle radiation of a radioactive. So a lot of times when they find like deposits of plutonium or uranium or whatever is, I guess not plutonium, but I guess uranium. I can't think of any other naturally occurring radioactive material. I think they're all naturally occurring mostly, but anyway, whatever. When they find radioactive things in the Earth, they tend to find a lot of helium also. But it's very hard to make, because you need sort of a nuclear reaction, or you need basically you need a nuclear reaction to make helium. It's not like it's bonded to anything. It's not like oxygen where you can just get it from water, right? It's a noble gas, so it doesn't tend to bond with things. So actually the amount of helium on the Earth is kind of finite.
We're running out of helium.
We're running out, and that's what I'm saying. And it floats, and it's lighter than oxygen, obviously. It's the whole point. So if it's lighter than oxygen, then if you release helium, it just floats to the top of the atmosphere. So there's not really a layer of helium, because it's so light that it just sort of ends up flying off into space or getting pushed away by solar radiation stuff. But it's so light that it just leaves, and because we can't really make any of it, and because the radioactive materials there's not that much, and they run out eventually. There's not going to be a lot of helium. I mean, eventually it's going to just get more expensive, and et cetera. But
Do we need helium for anything?
not really.
Okay.
Not that I know of. You need some weird isotopes of hydrogen for nuclear reactors, for fusion reactors.
Fusion. You can't really split hydrogen for much of anything.
So what's that?
Fusion is where you combine hydrogen with
Yes.
something else. Fission would be cutting something in
Yeah,
half.
yeah, yeah.
But since you don't really gain anything from cutting that in half, it'd have to be fusion, I think.
Yeah, yeah. But for some reason they use like it's a hydrogen with a neutron. I don't know why they use that, but there's a reason they use deuterium, it's called, and if you put another one, it's called tritium, and they use them for things. They use them in bombs, definitely, but they use them in other things too.
Okay.
And I don't know, and that's kind of running out as well. It's also not good for you. You shouldn't drink it. Maybe they use it in the cooling tanks, actually. Like the water, the cooling pools for nuclear. Anyway, I don't really know what I'm talking about, but okay. Should watch Chernobyl. We did talk about this. Really good.
Maybe Professor Z assigns for homework, we can find the time.
Yeah. It's only like 6 hours.
Yeah, it's not that much. It's a really good series.
Yeah. Sorry. Does anyone have any questions?
I'm good. honestly.
Good. I gotta watch that other video.
Yeah, the other video has all the homework on it,
Thank you.
which I don't want to just get into the habit of just like telling everyone to watch another video.
No.
But I don't actually want to
Do it again.
do this again with possibly making a mistake.
Oh, well, yeah.
I believe the one I did last time was correct. And this is the idea too. This is the point is the idea
Right.
mostly.
are you going to consider just if you ever have to TA this the next cohort for next year, you'll just be
Telling
sitting
them
down,
about the
headphones,
videos?
say, yeah, sure, just watch the video.
I've considered it.
Are you doing a second year?
Yeah.
Really?
They just said I can have it until I graduate.
That's good.
You're going to reteach them.
I guess they didn't officially offer it.
Oh.
Like, because they don't do that until. So I guess they could change their mind. But
Dr. Z doesn't get to choose though?
oh, he probably does. He told me like I tend to just pick people for the same people until they graduate. Like, all right. Do you have a question?
A few, yeah.
Sure.
So regarding degrees of freedom.
Yeah.
All right. So a degree of freedom basically refers to the geometric properties or the geometric arrangement of atoms in a molecule, right?
Yeah.
Thank you.
Yeah.
Booyahs.
So you guys. All right. So oddly enough, this book talks about degrees of freedom, but it doesn't actually define what a degree of freedom is.
Yeah.
So I just want to make sure that the degree of freedom I read about in my organic chemistry textbook 5 years ago
Yes.
is the same kind as the one we're talking about right now.
Yes. It's a place to put energy, basically. So, like when you think of kinetic energy, there's 3 places you can put the kinetic energy. You can put it in x velocity, x kinetic energy, y, and z.
Okay.
Right? If you said that if you were in 2 dimensions, like you were in like you could only move in 2 dimensions, there would only be 2 places to put your energy. That would be 2 degrees of freedom. So, does that help?
Okay. So let's say we're looking at methane, right? Which is CH4.
Sure.
So if that's the case, how many degrees of freedom would that have relative to H2O?
So that would be so if methane's like this. It's supposed to be 3-dimensional because it's like a triangle and then there's one behind hydrogen behind. So this is methane, and then water is like this. Well, let's look at this. First of all, both of these have 3 linear motion. So the x, y, and z, they can all move in x, y, and z, of course. So they have at least 3. This one can rotate around 3 dimensions.
Okay.
Because if you put a line like here, it can rotate like this. If you put a line here, it can rotate like this. Put a line here, it can rotate like that. So it's 3. So this has 3 linear, 3 rotational. And then what about vibrational? Well, this is where you actually have to look it up usually, because you can't. You might think, oh, this has like 2 vibrational because it can kind of go like this, right? Or it can go like that, or you can imagine like this one can move up and down, this one can move up and down.
So is there like a like the 3-finger rule or any sort of formula that we could try to use?
For vibrational?
Well, to figure out the total number just in general for any molecule?
No.
No, we just have to figure it out from experience.
No, you have to you should definitely be able to figure out the linear and rotational ones.
Okay, so the rule of thumb for linear then, what's that? Like, what question do you ask yourself?
Can it move in 3 dimensions?
Okay, are there any molecules that can move in 3 dimensions?
Molecules that you put in 2 dimensions cannot. But no. But if you mean like if it says it's a 3-dimensional, if it just says it's a normal gas, you assume that it moves in 3 dimensions. Yeah.
Okay, so this is based on an assumption that we get. So
Yeah.
If we have, say, a jar and we
Yeah.
have any number of gaseous particles in there and it's all the same molecule,
Right.
then we'd say, okay, at the very least, it's in a jar, 3 dimensions. It can move. It has at least 3 degrees of freedom from a linear perspective.
Yes.
All right. So for rotational, is it the same thing?
Yeah, so rotational is a little trickier because rotational is everything can rotate around. You can imagine it rotating around all the dimensions, but some of them don't do anything when they get rotated around some dimensions. Like imagine this is like diatomic, whatever, hydrogen, oxygen, whatever.
Yeah.
This can definitely rotate like this, right? But if you put like a line here and you imagine it doing this, it's actually not doing anything, right? If you slightly rotate it, can you tell the difference?
Probably not.
No, you can't because it's just, I'm drawing them as circles, but they're really points.
Yeah.
And this is a point, and they're connected with a bond, which is not really a line. And you say, now if I try to twirl it like that, like this marker. Now, obviously, it has some thickness, but imagine it had no thickness. This doesn't do anything. You can imagine, like, what's the moment of inertia of rotating something with no thickness, like this? Well, if there's no thickness, it's zero, because there's no resistance to. It's like something without mass, kind of thing. So there's no such thing as rotating. It doesn't mean anything to rotate a linear molecule in this dimension. But it can still rotate around this one, and it can still rotate around, if I put the other axis like this way, it can still rotate like that.
So,
So this has 2 degrees of freedom,
all right.
or rotation degrees of freedom.
So the first question for linear is, can it move along however many dimensions?
Yes.
The second one is, can it rotate along the axis of those dimensions?
Yes. So
Okay.
linear, basically always going to be 3
Okay.
degrees of freedom. And it's going to be rotational, whatever. It's going to be 3 minus, I would just say minus, I'll say symmetry.
Alright.
But what I mean by this, if this doesn't help you, then don't remember it. But what I mean by symmetry is like, this is symmetric along this axis. Meaning rotating it along this axis, which means twirling it like this way, doesn't do anything. It doesn't actually change it. If you rotate it, if I took this marker and I rotate it this way, that's changing it, right? It's actually changing, it's becoming a different shape, right? It's like turning.
Okay.
This is not, if this was infinitely thin, would not be turning. Nothing's really happening because there's nothing to turn in this direction. It's infinitely thin.
Okay.
So,
So the question is, if you turn it along an axis, will you notice it?
yes, exactly. Will you tell the difference?
Okay. So in the case of the x dimension, the x-axis, that doesn't apply. If it would rotate around the y-axis, it'd be the
Yeah.
same thing, though. I wouldn't be able to tell.
Why not?
Because if one of them is twisting it. Oh, I see. So at 1 degree to 360 degrees, can you tell?
At 1 degree and 90 degrees, for example.
Okay, in that case, so yeah, it works on the y and the z-axis.
Exactly, right, because this is the other one.
Yeah.
And then this is the other one. And you could always tell those 2 cases. That's 2 axes you can rotate around. So for water, this is for like
Hydrogen.
hydrogen, H2.
Yeah.
This would be 2. And then this is vibrational. I mean, he hasn't given you enough information in the book anywhere to actually tell.
Okay, I'm
I would say don't worry about vibrational unless it's in a lattice.
okay.
It's solid, which is a different thing. These are all gases.
Okay. So in that case, the reason I'm asking this is because I could be wrong, but the equipartitional theorem discusses different degrees of freedom.
Yes.
Wouldn't it be, so does this mean that we can expect the degrees of freedom to be given to us on the problem? Or are the degrees of freedom just a consideration we make in getting the final formula? I couldn't tell if that was...
The degrees of freedom is how you get, what you need the degrees of freedom for, is how you get things like a specific heat. So yes, if they ask you about, for a gas, I think you can assume that there's no vibrational.
Okay.
Because, and again, remember that graph with like at different temperatures, different modes become active?
Mhm.
The vibrational mode doesn't become active until very, very hot temperatures anyway. So you can assume it's not there. However, when you're dealing with a solid, so a solid has fixed molecules with fixed bonds, these can have vibrational at most energies. So these you do have to worry about, and if it's like a flat lattice, this has, well, how many linear degrees of freedom? 1, 2. I'm assuming it's just flat, it's 2-dimensional. 1 and 2, and then how many vibrational ones does it have? Well, it can vibrate in this direction and can vibrate in this direction. So this would have 4 degrees of freedom for a flat 2D lattice like this.
Okay.
And if it was a 3D lattice, then you would just have 3 linear motion, and then 3 vibrational too.
Okay.
So the way he's talked about it is that we don't care about the fact that there's vibrations in gases.
Okay.
There is, but they're not very important. Compared to the other ones, they're not very important.
Okay.
Let me say that the water and the methane both have 3 rotational.
because they're so distinctive that if you were to rotate them across the x, y, or z axes, you would be able to tell whether it's
Exactly.
1 degree or 90 degrees.
Exactly.
Okay.
Yes, that's a good way to say it. Yeah.
I got some stuff over here.
Sure.
You close at
Actually-
3 o'clock, right?
Yeah. Let me just
Sure.